and let us know if you have any technical issue or if the audio or video is not working. Please type in the chat. Also, if you want to ask any questions, again, type in the chat and we can unmute you and we can interact. So we're very happy that you're today, Karen Yeats from the University of Waterloo, the Department of Combinatorics and Optimization. And today we will talk about the combinatorics, Wilson loop, and diagrams. We're very happy to get that Karen in person. And also next week we'll have another in-person seminar. And
all right, thank you very much, Matteo. Thank you for the invitation. So I'm Karen Yeats. And I think it's super exciting that you guys have a combinatorics and physics seminar. Somehow in my mind, I always wanted one of those, but I didn't ever make one. So I'm going to talk about some combinatorics of Wilson loop diagrams. And this comes from 2 papers with 2 collaborators, Sushma Agarwala and Z. Fryer. The papers are now in the Canadian Journal of Math, but you might want to find them on the archive because that might be easier for you. So there are the archive numbers. Just first, let me just note that this is a different piece of combinatorics and quantum field theory than what I usually talk about. So for me, my usual story, it particularly involves scalar field theories, often 5-4, maybe quantum electrodynamics if I'm getting a little more physical. And in the scheme of sort of loops versus legs, I'm usually a high loop, low leg kind of person. So this is usual for me. But today, I'm going to talk about Wilson loop diagrams. So that's something from n equals 4 super Yang-Mills. It is predominantly sort of a tree level story, or certainly it's a high leg, low loop story. But I think that in some ways, both of these are toys, right? Because if we look out at the real world and we think things that certainly have the standard model very closely in them, then we see that both of these are toys, but they're toys in opposite directions because they make different kinds of simplifications. And so I hope that over time we can bridge between these things and make something so that we can understand the combinatorics really of actual quantum field theories in the world, physical quantum field theories. Let me just finally make a small pitch in terms of if you do want to hear more about my usual story, I have a note, is that I will be giving a seminar at UMass Amherst. Since I came here in person, I thought I might as well. And this is in their discrete math seminar. And it's Friday. I think it's also at 9:30. And it's going to be on chord diagram expansions, which are a alternate expansion instead of a Feynman diagram expansion for quantum field theories, a chord diagram expansion, which is very pretty and has some really nice properties. And I will talk about that on Friday. So if anyone is interested, I don't have the link on me, but I believe it is also hybrid like this. So if you are here and feel like taking a short drive up to Amherst, you'd be welcome to come in person, or otherwise you can catch the Zoom link. Okay, so what am I actually talking about today? Because I'm not talking about that. I'm going to be talking about Wilson loop diagrams. So let me just give you an example. So what am I going to do? I want to have some numbers. Actually, it's kind of like a chord diagram, but we don't want to really think of it exactly as a chord diagram. So I've got some vertices along a circle. That's the Wilson loop itself. And then I have some propagators, which in the case we're going to talk about today, go from an edge here of this outer loop to another edge of this outer loop. So something like this, something like this, something like this. So there's an example of the kind of diagram that we're going to talk about. We're going to be interested in non-crossing diagrams, and we're going to be interested in diagrams that have a certain density condition. You're not allowed to have too many propagators all squashed up together. And the actual condition is if you have some set of propagators, the support is all the vertices that are the endpoints of the edges that the ends of the propagators are on, and you don't want that number to be too small, the number of vertices that it's supported on. All right. So these are the objects that we're interested in. What is the idea? Where the heck do these diagrams come from? Well, I think some of the people in the audience already know this very well, but let's just briefly say what we're talking about. So the outer loop is in fact the Wilson loop that you might see in a initial physics context, and the idea of the loop itself is essentially duality, right? So if you have some particle scattering, right, you've got some things coming in, some things going out. Okay, well, what do you know? You know you have momentum conservation. So if these PIs are the momenta, then you know these are some vectors, say some 4 vectors, or whatever space you like to work in for your space-time. But because of momentum conservation, if I think of them now literally as vectors and put them head to tail, then it has to be the case that you get a closed cycle, because that's momentum conservation. Okay, and that's the Wilson loop. Okay, so that's what our outer loop of our diagram is. And in fact, the bigger picture is also duality. So when folks work on these maximal helicity violation and next to maximal helicity violating, etc. diagrams in twistor space, when you take a dual, then you're going to get something that's basically our Wilson loop diagram. So that's what we're studying. Okay, so that's all nice. What do I want to do with them now that I have them as objects? I want to build a matrix out of them. And how do I do that? Well, let's take the same example we had up here. And what am I going to do now? I'm going to make a matrix. It's going to have as many rows as there are propagators, so 3 in this case, and it's going to have as many columns as there are vertices, so in this case, 8. And what do I want to do? Well, at the ends of the vertices that support the propagators, in the sense I said before, I want to put a non-zero entry. All right, so here, if I look at this guy here, well, I'm going to put something here, nothing here, something here, nothing here, nothing there. And similarly, the second guy is going to give me something like this. And this last guy over here is going to give me something like this. That's not very good. Okay, so I build a matrix. And now I think for this audience, I don't really need to tell you the positroid story, but I'm not sure exactly who's in the audience. So just very briefly, if I think of this matrix as representing a matroid, first of all, so it's the representing matrix of a matroid, but it's not just any old matroid. It has a property that for appropriate universal choices, you can make all of the subdeterminants positive or non-negative, and that's the positroid condition. And positroids, as many of you guys know, are combinatorially extremely beautiful and also somehow physically very relevant. So here we are, we have Wilson loop diagrams and we have some nice positroids. Okay, well, we can ask some questions. The first thing you might notice if you play around with all these things is that they're not always different positroids. And so here's an example. Let's just draw the 2 diagrams that go with these guys. So here's 2 matrices, and if you just reverse engineer what I said before, well, what's this saying? This is saying it's going between here and, well, not that guy, but over here. And this guy is going here to here. What's this one? Well, it's almost the same. It's going from here. But now the second one is different. It now goes like this. And again, if you're a little bit bored, you can sit down and think about what the non-zero minors have to be of this guy, and you will see that in fact these are the same positroid. Okay, well, why is that? Let me draw a couple more examples to give you a bit more of an intuition of why this is true. So here's another pair that give the same positroid. All right, what am I going to do? I'm going to do this. Or I could also do this. Okay, and there are many more examples. Maybe I won't spend the time drawing a bunch more examples right now, and I will just cut to the chase and tell you what the answer is. So the key is basically triangulations. And so let's go back to our first small example. What did we have? We had this guy. And now what do I want to do? Well, let's sort of switch the edges and the vertices along the outer cycle. And so if I change color here to do that, let's put a vertex here, 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 a nice big fat vertex where those two propagators now meet. And these now have just become, oops, what did I do wrong? Oh, I did something wrong. I didn't draw my diagram correctly. So if I'm trying to do the diagram that I had before, I need this guy to be there. And now going back, now it's going to work correctly. So there's still this fat guy, there's still this guy, now there's this guy and this guy. And so what do we see? We have some polygon dissection, which we want to call tau of W. And now some section of this polygon dissection might be triangulated. So in this case, this section of the polygon dissection is triangulated. There could be more than one piece that's triangulated. But anytime you have a triangulated piece, you can retriangulate. So in this case, there's only one retriangulation. That's the one other triangulation of this same guy. And then if you convert that back into the Wilson diagram, what do we see? Well, we see exactly the other one we had that was equivalent. And in fact, that's the theorem. So diagrams are equivalent if and only if they're retriangulations of the triangulated section. There it is written down, but it's exactly what I just said. The notion of these exact subdiagrams, which are the ones that are triangulations when you move to the polygon dissection, they're important for that, and they're kind of the only way. They're the ones that are critical for that initial density condition. They're exactly the triangulations, and somehow you don't care what the actual structure inside that triangulated piece is. As a consequence, that means you can count easily how many equivalent diagrams there are given a diagram, because there's Catalan many triangulations. And so you just take the sizes of the different triangulated pieces and multiply the appropriate Catalan numbers together. And there you go. Okay. But now, as soon as I had polygon dissections, some of you guys were probably thinking about associahedra. Because associahedra can also be defined by polygon dissections. Okay, so what's an example? Well, of course, no one ever draws very many associahedra by hand because they get pretty annoying pretty fast. But if I'm going to draw something by hand, maybe I'll draw this little pentagonal one. So how do polygon dissections make associahedra? Well, here I've got a dissection, and now if I take out one of the edges, then I'm left with a piece over here that I could triangulate a different way. And I do that over here. And then going all the way around, the vertices and the faces of all the different degrees can be associated with these polygon dissections with different numbers of chords. That's all fine and good. Like this. And then I have to go this way. You guys can catch me if I make a mistake. Certainly could happen. I don't think I've made one yet. And I'm almost done. Of course, there's really one more, because there's just a section for the whole thing. Okay. And I'm not going to actually draw the next guy out, but because it's going to be handy later, let's just draw the next issosahedron. Okay, let's do a better job than that of drawing the next size issosahedron. And I'm just going to label one of the square faces because it's going to be handy later on. So let's see, what do we have here? We have pentagons and squares at the next size up, as I think probably everyone in this audience knows. Here's one of the square faces. Square faces. And then there's another pentagon back here and another guy like that. And so these are going to come from hexagonal polygon triangulations. So for instance, maybe I've got that guy there, in which case I didn't draw the right thing next, in which case, well, what could I have here? I just have to swap one of them around. So I could have like this kind of shape. And then down here, I could move it over to the other side, have something like that. And then over here, what will I have? I'm going to have the other guy. Okay, now this is where I have to not mess it up. So I'm going to keep this one. It's that guy. Okay, so there you go, issosahedron. And because I am going to say something about parallel faces in a moment, I just want to fix which realization I'm interested in of this issosahedra. Of course, there are many, as most of you know. This is one of the standard ones, and it's the one that is going to be useful in this case. All right, so we're just taking a convex hull of these sort of these area vectors, sort of thing, Anyway, what is the point? The point is now, by the retriangulation rule that I said before, you can look at what does it mean to be an equivalent Wilson loop diagram. Well, if we just pick up this example again and bring it down, well, we see that if I've retriangulated a section somewhere, so to get from here to here, what did I do? I retriangulated one of those little blocks. To get from here to here, I retriangulated one of those little blocks. And so if I took one of those red edges, what's that going to be? The red edge is going to correspond to removing the one that gets moved. So that's going to correspond to, so I guess let's write that guy in. Oops, let's write that guy in correctly. So this is just this guy. And now what's this other red edge? It is, and here's where I hope I didn't. Oh, I did mess it up. Okay. Well, this is how you tell when you messed it up, because then the next thing you want to say doesn't work. This isn't the correct, I didn't put the correct guy there because, okay, what's the common thing between here and here? It's, what did I do wrong? did something wrong with my example. Okay, maybe I don't want to show you this example because I did something wrong on it. Anyway, what I want to get here is this one. Oh yeah, that's correct. Now that's going to work because this guy is now this one. And so you see the red edges are exactly two guys that differ only by a triangulation, because the part that didn't differ by a triangulation has already gone away. And these are two, in that realization, these are two, in fact, parallel edges. And the same will be true for faces of every dimension. So if you're parallel, then you are an equivalent Wilson diagram. So that's kind of cute. Okay. Well, we were talking about the faces of different dimension. Maybe it's a good time to talk about dimensions of these positroid cells, because that's also something that you can read off combinatorially from the Wilson loop diagram, and that's kind of nice. And this is actually the history. In many ways, this is the history of how I got involved in this project. So now, many years ago now, more than 5 years ago, quite a bit more, not quite, maybe 10, I don't know, many years ago now, I was at a conference and in Mainz, and Sushma was there, and she said, hey, I have this little problem that I'm trying to figure out about proving the dimension of these guys. And it said, oh, that looks like exactly the kind of combinatorial problem that I really like, because personally, the kind of problems that really suit my taste are the ones where you play around with little pictures and make some patterns happen, right? That's my favorite kind of math. And so, you know, I said, I think I can prove this. And sure enough, you know, it ends up being the way I saw it, a kind of ugly induction, but you can read it off, and that's kind of nice. Now, in the meantime, so I wrote some notes and then sort of forgot about it for a long time. So I was thinking about other things. And in the meantime, in work with Cameron Marcotte, Sushma found a more geometric proof. But there's still something really nice about seeing it combinatorially. So I'm going to show you how to see the dimension, to read off the dimension, or to understand the dimension combinatorially. There's not much to read off. The answer is 3 times the number of propagators. But how do we see that combinatorially? Okay. Well, the answer is to look at the Lie diagram. So as again, I think everyone here, there's a lot of positroid people in this audience. So I think you all know that of the many very nice combinatorial objects that you can see that are in bijection with positroids, one of them is the Lie diagram. And so now if I'm going to go right back up and do an example, I'm going to do an example that's not too big because I don't want to spend too much time just computing examples. So let's just do this one. Now, what sort of Lie diagram are we going to make? Well, there are 6 vertices and 2 propagators. So our diagram here is going to have 2 rows because of the 2 propagators. And then the total size here is going to be 6. So the big shape in which we want it all to fit is this one. And it turns out this particular diagram is in fact going to give exactly that shape. And then we'll fill in our pluses. All right, how do we do this? Well, I'm actually going to go through the Grassmann necklace in the meantime. So let's draw a Grassmann necklace as we're going through. So here's what I'm going to do. I'm going to start at vertex 1. And now I'm going to go along the circle collecting propagators as soon as I can. But once I've collected them, they're gone and I don't have to worry about them anymore. So I can collect this propagator here. Now I can collect this propagator here. That's the first time I get to collect it. So 1, 2. And that tells me that this is in fact the shape I want for my Lie diagram. Okay, what's next? So I've done that guy. Now I'm here at vertex 2. Okay, well, I'm allowed to collect anybody in the support. So I can collect sort of all the way from this interval just before the previous vertex up to the next vertex. So I collect the first guy I can in that interval, which is this But now I've already collected someone at vertex 2. So I don't get to collect this guy as well. This guy has to go to vertex 3. And so 2, 3 is the next term in the Grassmann necklace. And that tells me where to put a plus in here, because I got to send the 1 down to 3 there. Okay, and we keep going. So let's keep going. If I'm here at vertex 3, well, I can collect this guy, so that didn't change. And now that guy's all used up. So by the time I get to vertex 4, in principle, I could collect either of them, but one of them's already collected. So I collect this guy instead. Okay, and so this is 3, 4. Okay, so I got to get a 3 and a 4, so I got to put these here. What else? I'm at 4. Now I can collect. This guy hasn't been collected yet, and it comes first, so I'll collect it. And I collect this guy over at 5. Okay, so I need to get 4, 5. I need another color. Okay, so now I'm here at 5. I'm going to collect the first guy I can, which is this one, because it comes first in that interval. And now I keep going around. I've already got that guy. Oh, but I don't have this guy yet. So I collect it at 1. So now I see 5, 1. Okay, so put that there. And then we're almost done, because I'm here at vertex 6, but I don't get to collect anyone from vertex 6. There are no propagators there at all. So I'm back to getting this guy at 1 and this guy at 2. So I'm already back to 1, 2. And there I'm good. I've got a Grassmann necklace and I've got my Lie diagram. Okay. And now it's easy to read off the dimension from the Lie diagram. It's just the number of pluses. So really what we want to understand now is how these propagators are putting pluses into the Lie diagram. And if we can understand that, then we have a combinatorial proof that the dimension is what we think it is. Okay, well, we can do that via an annoying induction, which I'm going to now briefly sketch for you. And you will see that at least conceptually, it's not that bad. Okay, so what am I going to do? There's a couple things I can do. First of all, I can remove any unsupported vertices. So if we go back to the example, what's something like that? That's like number 6. It didn't do anything, right? It didn't. It's one of these situations where you just get 2 Grassmann necklace elements that are the same, and so that doesn't do very much. And here it just gives me an empty column of zeros, so that doesn't do anything. Well, if I rotate or flip the diagram, that's not going to change the dimension, which you can show, but it's not surprising. And then I can do that until I have one of 2 situations. So if here's my last guy, 2 situations of a rendering bug. Okay, so if here's my vertex n minus 1, my vertex n minus 2, or my vertex n minus 3, and then I have a propagator here, but I don't have, and I'll highlight this in red, there's a region in here with no other propagator ends, and it goes all the way to there. Or, so sometimes I can get that situation, or I can get this situation. Where it might be that I can't go all the way to n minus 3, but if that fails, then at least I have another small propagator. Okay, so this area is empty all the way down to here. That doesn't make sense. It's got to be all the way to there. Okay. There could be other guys here past this one on that same edge. Okay. So by removing the unsupported vertices, I know I've got some small propagators. And then I can rotate or flip so that there's a small propagator in that last slot, like coming up to n. And then I have at least some control of what comes next. Either there's nothing or there's another small one. All right. And then once I've got that, then I want to use induction, removing that last propagator. And what you get on the Lou diagram is the following. There's some region in the Lou diagram, which I'll call this A. And then there's some little strip. And then there's some region B. And then removing that one guy. Well, sorry, I guess this is the other way. This is no, okay. Anyway, I'm going to draw it and then I'm going to say which way is which. Basically, you're moving between this shape and this shape. So here you've got one more row. So this is the side with the one more propagator. So I guess in the induction, I'm really thinking about going this way. Here I have one more propagator. I remove it. That's going to correspond to putting in, because the total size of the overall box still has to be n. If I have one fewer propagator, I have to have one more row, and that row is going to be here. And the A and the B parts stay the same. And you can understand explicitly how any pluses from this section and the pluses from this section relate. And then that tells you what you need to know. So you need to know that you get exactly, yeah, sorry, I didn't say this quite right. You need to know that you get exactly 3 new pluses. You do get, there's exactly 3 new pluses here. And then you need to know what happens to these, but they in a controlled manner. Some of them get sort of shifted over, but they move in a controlled manner. So you know exactly what happens to the pluses in this column, the pluses in this row, and then you have your answer. Yeah, so that's kind of nice. Okay, I'm going to tell you one more thing that you can do combinatorially with these guys, which I think is also very cute. And that is, I'm going to tell you how to read off the denominator. So let's think back to the original problem. Why did we have these diagrams? They were coming from some next to maximal helicity violating diagrams. And so, I mean, really, okay, they're not Feynman diagrams, but there's something that's taking the same role as Feynman diagrams. So you should be expecting to build some sort of, well, integrand in general, or just some sort of term if you're when you're at tree level, out of these guys. And sure enough, that's the whole plan. And in the classic way, you know, each propagator is contributing a factor and so on. But now the question, well, one of the important questions is what the denominators of those things look like, because of course the denominators are going to tell you where the poles are, and you need to physically, you know, there are no poles overall, so they must cancel, and you would like to combinatorially understand how they cancel, right? This is a classic story, which I know many of you guys also already work on in your own representations of these things. So being able to read off the denominator is very useful, because that lets us read off where the poles are. And we can do that using just a variant of what I already told you, in a very nice way and in a way that lets you prove things about it. So I'm just going to do this again with an example. This example is going to be my longest example yet. So if you don't like examples, you came to the wrong talk. So let's look at this guy. Okay, and now I won't hassle you by drawing it 7 times. I will copy. Oops. I will copy it badly. Okay, there. How many of those did I make? Okay, there we go. Now I've got the right number. Just think, if it had been a Blackboard talk, you'd have had to watch me draw that a lot more times. Or I would have had to do a smaller example. Okay. Now, what were we doing before? Remember that thing we were doing to build the Loo diagram? We were collecting the propagators as we went around. So we're going to do that again. So let's collect this propagator here. This propagator gets collected here. This propagator gets collected here. That would give me the first term of the Loo diagram. Sorry, the first term of the Grassmann necklace. Okay, I don't actually want the Grassmann necklace right now, but I want to keep making these things. And we'll see why in a moment. As I keep going around, and I always just take the first, take the propagator as soon as I can. Okay, now you might have noticed 3 doesn't support anything, so this is exactly the same as the previous one. Okay, but now it's starting to be different again. You guys can also catch me if I make a mistake. And that includes the online people. You can also catch me if I make a mistake. Although I think you have to catch me in the chat and then make sure Matteo sees it. All right. Okay, phew, that's almost done. Okay, now it's actually done. Okay, now what? Well, what I want to do is I want to see which ones have changed. Okay. So here, let's get another color. This guy, it used to go to 1 and now it goes to 2, so it changed. This guy used to go to 2, now it goes to 5, so it changed. But that guy didn't change because it still goes to 4. Okay. Well, I guess the last thing I need is I actually need the matrix. Let me write down the matrix for this thing. And we're going to take a particular, minor of it based on which guy's changed. So here's the matrix. I won't bore you too much with this matrix. So here what's happened, the first propagator and the second propagator have changed where their ends are. And now I'm going to, in the second one, I'm going to say, well, where did the ends go to? They went to 2 and 5. So for that first pink example, I'm going to take the first 2 propagators and I'm going to take columns 2 and 5. So 2 and 5. Okay, and I want to take the determinant of that minor. The determinant of that minor is B times G. So the difference between these 2 guys contributes BG. Okay, let's do the next few till we see what's going on here. Okay, to get from the next 2, I better highlight in a different color. 4 stays the same, 5 stays the same. The only thing that's different is this first one goes from, it used to be 2 and now it's 6. So now I look down here in the matrix, that was propagator 1. And all I care about is the 6th column, 1, 2, 3, 4, 5, 6. So all I care about is this C. Wait, what did I do wrong? It should be. All right. Well, now notice this guy and the next guy are the same, so there's nothing to be done here. You just get a 1. And it continues. What's going to happen next? We have, I think on this one, everybody changes, right? Yeah, everybody changes, and they go to 5, 6, 7. So for this one, let's just take another color. I have all 3 of them, and I have 1, 2, 3, 4, 5, 6, 7. So I have, I always manage to do the wrong thing. I have this minor now, this whole minor. Okay, but that's not too bad to take a determinant there. It's just LH and a D. and so on. So here, I'm not going to bore you with every single detail here. Here, you're just going to get an EJ minus FI, because for this one, you just have this minor. Going from here to here, you're going to get, no, I did the wrong one. EF plus, yeah. I shouldn't have skipped one, because if I had done it, it's between this one and this one that you get the EJ minus FI. Between these two, you just get I. And then finally, going from the last one back to the first one, you would get an AF minus BE times K. It's the first two columns and the fourth column, as it had to be. And so then what is the denominator? You just multiply all those factors together. And so these are pulling out exactly what you get in the denominator, where the pulls are going to be. And notice something that happened as we did this. Occasionally, we did in fact get terms with as many. Occasionally, we did in fact get minors that had as many rows and columns as propagators, but we never got a determinant that actually looked like a generic 3 by 3 determinant, right? The worst we got are 2 by 2 determinants and 1 by 1 determinants. And that in fact is general. Because of the structure of the diagram, you can in fact never get something full enough to give you more than a 2 by 2 and a 1 by 1. And that's true at all dimensions. So, well, that's kind of nice. And it's something that you can work out extremely explicitly just by how the edges are changing as they go around the cycle. So that's what we did in those two papers on Wilson loop diagrams. Just to briefly say, since I have a couple of minutes, that we're of course still thinking about some of these things, even though I work on a lot of other things, other aspects of combinatorics and quantum field theory as well. But we are right now thinking a bunch about ways to diagrammatically characterize all of the boundaries of all codimensions. And that gives us some nice new types of diagrams, because you get to combine together propagators into more complicated objects. And it looks like there's going to be a very pretty diagrammatic that hopefully you'll hear about in another, I don't know, some other time. Depends how quickly we get it all done. Okay. I think I'm going to stop there, and I think you can certainly put questions in the chat, and we can probably get it working so that you can ask other kinds of questions, auditory questions as well. But I will leave the details of that up to the table.
Thank you very much, Karen. Let's thank the speaker. I have to be close to the microphone. So if you have any questions, you can also turn on.
I could turn on the sound here.
Yeah,
as long as we don't get feedback. But I guess we shouldn't if that isn't working.
Feel free to unmute yourself if you have any questions and ask now. Thank you. I can also get this.
I have a question, if that's okay. Can you hear me? Yeah. Yeah, I guess I would be most curious about the combinatorics of the sort of generalized chord diagrams corresponding to boundary strata. I mean, maybe you're not ready to say much about it, but I'd be curious if you have anything you can say along those lines.
So a couple of things happen. The simplest thing, which I think is already written in some other places, is that you can take ends to vertices instead of being on edges. But you can also have them combined together. So when two propagators have an end on the same edge, they can be merged together, and then you get a propagator with 3 ends. You can get propagators with arbitrary numbers of ends, but you can also do it. There's also a sort of some swapping operations. It's sort of, I don't know. It's like when the chromosomes cross, like a piece of one goes to another one, and so you get a sort of exchanging operation. And maybe I don't want to pin down exactly, because there are still some details about what happens for arbitrary codimension, but there's going to be, there are a number of moves that work, and I think we're going to have a full inventory of moves relatively soon.
Thanks.
Are there more questions from the audience? Also, feel free to ask if you have questions here. Meanwhile, I have a question.
Sure.
Could you repeat again? So, if you set to 0 any of these factors in the denominator, you access the codimension 1 boundaries of this positroid cell.
Yeah.
Okay.
Yeah.
And so the connection to the when you compute n equals the amplitudes in n equals 4, can you repeat again what's the connection? Because I'm familiar with the BCFW representation, where there are each BCFW term is associated to a positroid cell, and then the sum of these codimension 1 boundaries of the positroid cells are giving poles of the amplitude. But some of them could be, I mean, if you think about, I don't know if I'm familiar with the amplitude picture, but if you think about these cells mapped into some other space which actually encodes the amplitude, some of these codimension 1 boundaries might be higher codimension in the amplitude, and so they might not correspond to poles, like codimension 1 pole. So I was wondering whether there is any.
Yeah, so there's a very similar picture here, because again, each one of these diagrams is corresponding to a positroid cell. Now there is this duplication, so you have to take care of that, but then you want to try to glue them all together. And that sort of more geometric picture is something you might want to ask my collaborator Sushima, as she's worked with some of her collaborators on that as well. But there's a very similar picture, and again, yes, sometimes the codimension drops more than you would think, and that comes down to when there's sort of excess density, when you make one of these moves, sometimes you end up with too many propagators concentrated together, and that's when you can get a higher drop in the codimension. So it's a very similar picture, which is not too surprising because it did start from taking, well, not exactly the BCFW diagrams, but sort of twister analogs and then dualizing. So it is actually a different story, and there are some important geometric differences, but it is quite analogous. Yeah.
Okay. Yeah. So here you are in twister.
Yeah.
Twister side of the story, not the momentum.
Yeah.
Twister side of the story. Or.
Ooh,
well, okay. Like. Okay. Let's see. Well, it's related to by a T-duality.
Yeah.
Which side of the story? Well,
I'm not sure. I'm not sure in your language.
I think maybe I know, because you said these are of dimension 3 times k, right?
Yes. Yes.
Okay.
Yeah. So.
I mean the.
Yeah, I'm not sure exactly where it lives in your story. But,
okay.
But yeah.
Right.
Sorry.
Yeah. Thank you. Okay. Do you have any other questions? I'm just gonna get.
I think I can open the chat here, possibly.
Okay, since there are no more questions, another question maybe is there a way to read dimensions from the matrix representation instead of going to the Lie diagram, or is there a way to understand like the kind of the degrees of freedom from the rows?
No. So yeah, that's another, especially when you start getting into the boundaries, that becomes a very interesting question, because you sort of want a minimal representation of the matrix, right? Where you don't have any spurious free variables.
Yeah.
And that again comes down to a slightly different density condition, that if somehow, so as you see, you don't get a unique representation because there's more than one diagram. And when you get into looking at the boundaries of various codimensions, you get even more of that. But some of them are somehow the best or the minimal best behaved ones. And those ones will just, when you read off the matrix, you will just get the right number of free variables.
Okay.
So I guess yes, but it ends up being a little bit complicated.
Okay. Thank you very much. So if there are no further questions, we can thank the speaker again. Thank you. Thank you very much, and I hope to see you next week. Bye.